Good afternoon, everyone. It's great to see a lot of my current colleagues, former colleagues, bosses, friends here. So thank you for coming out to listen to me speak. I'm Aditya Ravichandran. I also go by Adi. I'm a senior engineer in the machine learning platform team at Loblaw Digital. And I'm going to be talking about enabling ML model observability to drive real-world outcomes. So what is model observability? Here's a definition that I came up with. It is the ability to monitor, troubleshoot, and explain a model's performance throughout its lifecycle. That is to say, from research to development to testing and in production. So how do we enable that? We record model inputs and outputs. Well, it's simple, right? Well, we can conclude the talk right there. Thank you for attending. Well, jokes aside, it is indeed that simple. But in the context of a large organization with multiple machine learning use cases built by multiple teams of machine learning engineers, or MLEs, achieving this can be quite challenging. So essentially, well, also the use cases are just growing, by the way, like in our team. So essentially, that's what we're going to talk about today. How to enable model observability in a large organization with many machine learning use cases and teams to drive real-world outcomes. And how can we achieve this while making observability easy? So here's how the talk is organized. First, we will discuss the context in which we operate. We will go through what we do at Loblaw Digital. Then we will look at some common architecture design patterns we use so far to achieve observability. After that, we will discuss a better solution than the one we just discussed, and our vision for the future. And finally, we will discuss how we are rolling this out. First, let us look at the context in which we operate. At Loblaw Digital, we build digital and e-commerce experiences for all Canadians. Well, what does that entail? It entails building shopping experiences, online shopping experiences for grocery, clothing, and beauty products, and the platform that powers digital pharmacy, grocery delivery, and the loyalty program of Canada's largest retailer. This also means we're responsible for the user experiences of Canada's most recognizable brands, like Shoppers Drug Mart, or Pharmaprix if you're in Quebec, Joe Fresh, PC Optimum, PC Express, to name a few. Well, hopefully, that gives you a sense of the scale and the real-world impact of products we build. Now, you might be wondering, how does machine learning play a role in all of this? Well, let's take a look at that. We build models for multiple use cases. Specifically, we work with product domains for digital content, such as search, recommendations, ads. We also work with supply chain domains, such as inventory and order fulfillment. We have multiple models in each of these use cases and domains. And across these models, we serve thousands of inferences per second to serve millions of Canadians. And to ensure this happens very smoothly, we have several teams of MLEs working to create, implement, productionize, and improve all these models. Well, now you may recall that I said I'm part of the ML platform team. What is the ML platform, and why is it needed? Let's take a look at the team's official mission. It is to empower MLEs to productionize ML models and services by providing the best development experience through a self-service platform. That's a mouthful. Well, so let's focus just on the self-service platform part. Some of its components include standardized tools for model training and serving, internal packages, templates, scripts that abstract away deployment and runtime permissions, containerization and artifact versioning, much, much more. It also includes infrastructure such as highly available key value stores, Airflow instances, a data lake, as well as the cost and performance monitoring infrastructure for all of the above. The goal here is to provide the most out-of-the-box experience for MLEs as possible, freeing them up to work their magic and solve business problems using machine learning. And being structured this way enables us to seamlessly expand the number of use cases, the variety of use cases and domains where ML is applied, as well as to add more teams of MLEs to facilitate this expansion. Now, that should give you a 10,000-foot view of how machine learning and machine learning platform fits in at Loblaw Digital. Now, let's get back to talking about observability. Loblaw Digital has been building, using, and improving models for more than half a decade now. So it should come as no surprise that there are existing mechanisms for measuring these models to facilitate their improvement. And broadly speaking, there are two design patterns that are followed to implement these mechanisms, and let's look at them one by one. Here's an illustration of an existing pattern, and let's call this pattern number 1. And this is typically what we see in models which determine what products are seen by users when they shop online. We see that there is a front end, either a website or an app, with which the user interacts. The app then requests content to some backend services. This could be product information or content services, or the shopping cart service, and so on. And this backend service, in turn, requests an inference from a machine learning model, which is wrapped in an API and exposed as a machine learning service. It could be a search, recommendation, or ads model. And the inference from this model is then used to determine what content is delivered to the user. And when the user interacts with the app by viewing or clicking one of the products or pages in the context of the delivered content, this user interaction is then captured in the form of event data, along with information about the model that was used for this content. And voila, with this architecture, we can now measure model performance, gain insights on how the model is doing and whether it's doing well or whether we need to make changes to it or not. To drive it home with an example, let us look at what this data might look like. Here on the lower left, we have a recommendation carousel. So when you're browsing online in any of our online stores, you might see a box that says, you may also like these products, and a whole bunch of recommended products show up. And on the bottom right, we see data corresponding to a user viewing such a carousel and then clicking on one of the products in this carousel. So the query result that you see on the right provides valuable information which we can use to measure both model performance, such as NDCG, precision at K for recommendation model. Also, we can use this for product or business metrics, such as clicks, click-through rates, and so on. And we can also measure some drift metrics from this data as well. So with the architecture we just discussed, all this information is captured through event data corresponding to the user interactions, and it is available in one table. As a note, we will be using the same example on the bottom right when we discuss other architectures as well, just so that there is continuity. Okay, so now let's look at some pros and cons of this design. So the pros. From the perspective of an MLE, we're able to measure both statistical metrics and to measure model performance, as well as business metrics such as clicks and sales to justify the return on investment for the model. There are also fewer components to maintain by the MLEs. You can see that in this pattern, the MLE is only responsible for building the model, not a simple task, but fewer things to do. Building the model and then building the dashboards to measure the model. And the cons, the development work and updates and deployment of any changes to the model, even minor changes to fields in the model output to measure these models are tightly coupled with external teams. And we would need sign-offs, end-to-end testing, release coordination with multiple teams. And this in turn could be affected by capacity limitations and whether other teams are busy or not. Now, let's look at another pattern. Let's call this pattern number 2. We can see that it's similar to pattern number 1 in that the backend service requests an inference from the model. This could be a backend that provides inventory details to an internal tool for stores, for example. And in this case, instead of relying on the backend, the model to ingest data into the warehouse, as you see at the bottom, the model logs the inputs and inference to an asynchronous messaging service. This data is then processed and ingested into a data warehouse to be used in dashboards. The difference from the previous pattern here is that instead of passing on the model-related information to multiple services to be then used in the warehouse, we're directly ingesting the inputs and inferences into the data warehouse. Let's look at the pros and cons here. The pros are that there's much less dependence on external teams compared to pattern 1, with decoupled development and release cycles. The biggest con here is that there are a lot more components for the MLEs to maintain. This takes away time and capacity to focus on improvements to the models, which sort of kind of defeats the purpose of model observability and making it easy. Another con is that we're only able to control the capture and recording of the model-related data, the versions, its inputs and outputs. While this makes measurement of model performance and drifts easy and owned by the MLEs themselves, measuring business metrics would require additional steps to discover relevant data sets, typically owned by other teams, and understanding what this data means, and then writing the queries in SQL to get the right metrics that they need to show the return on investment, for example. So, can we do better? What is a better solution? And we asked ourselves, how can we empower ML teams to focus on developing and continuously improving models in a flexible and independent way, while also being free from maintenance responsibilities? Shifting the framing of this a little bit, how can we incorporate ML observability into the ML platform with a view to simplify, standardize, and lighten the load on MLEs? While thinking through the solution, we took learnings from the experiences with existing designs, and we wanted to keep the ease and flexibility of setting up the metrics, reduce, if possible, remove coupling with external teams, processes, and reduce maintenance overheads. And we thought, if you could make it even better, what if we added alerting and made it available on metrics such as anomalies or drift, and have it configurable by the MLEs for each model? So we added that as a requirement as well. When we were brainstorming our vision for this, our engineering teams across the organization that own various front-end and back-end systems were onboarding Snowplow. Briefly, Snowplow is a powerful analytics suite. It's a powerful suite of tools that helps us record user interactions and user behavior so that we can perform analytics on this data. So we thought, instead of finding a way to solve everything, why don't we build our ML stack to work alongside the Snowplow analytics stack? Furthermore, we had already standardized our ML stack to run on the powerful, flexible, and open source suite of tools built by Selden. And what if we extended this so that we ingest model inputs and outputs into our data warehouse to enable observability? This way, we can achieve some division of labor. So this is how our vision for the ML stack looks like. We are already familiar with the models sending inputs and their inferences elsewhere, asynchronously. Here, we landed on building a centralized logger service that is designed to be flexible enough to be used by all models at Loblaw Digital. This service then logs this model input and inference data in a structured format into our data warehouse, from which we can build dashboards. What's more, the ML platform team will own and maintain all of this infrastructure. We will also design and build templated base dashboards from which MLEs can fork and customize dashboards for their models and use cases. This way, the teams of MLEs can focus on the models, and inner workings of the stack is abstracted away from them. And going back to our familiar example, in this case, the model-related data will be coming from the ML stack, and the business and product-related data will be coming from the Snowplow stack. So this is great. Now, how do we roll it out to a big organization such as Loblaw Digital? We started small with one project with MLEs who build models for ads. But we wanted to implement an end-to-end solution that works for the team where both ML model metrics as well as business metrics such as click-through rates and ad spend are measured. While working on this, we wanted to build out the core components we envisioned: the centralized logger, the log structure specifications, and the pipeline sync to the data warehouse. This time, for this project, we built custom pipelines for metrics. These are not flexible templates in order for us to be able to meet deadlines for this project. We will take this up later. And here are some of the results. Well, while we already saw an example of data that could be used for model metrics such as NDCG and precision, I wanted to highlight some of the real live dashboards that we built for this project that enabled us to show real business impact. And on top, we see some business metrics such as click-through rates, sales, spend on ads, and so on. And on the bottom, we see the real live dashboard from an A/B test for multiple models we were running for this project, still looking at some of these business metrics. Taking it to the future, in the ML platform team, our strategy is to take new components from project to platform to projects. What this means is that we work on a smaller scale, one project, like we discussed in the previous slide. We then make it generalizable and then roll it out to other projects. So in phase 2, we're working on a spec for templatable pipelines and dashboards that we saw in our vision. And some of these specifics of this is we want to have a standardized unique ID for each inference so that it's easy for our MLEs to use this to be able to discover other data sets to join with. And then templated pipelines, like we discussed. We also wanted to, we didn't talk about it much, but we wanted to standardize alerting. If we had any metrics for drift or anything else that we want to measure, we are working on incorporating alerting into our dashboards. And we also want to drive adoption. You know, our MLEs are very busy building models for their use cases, maintaining and improving previously built models. We want to help roll this out to all models by making it easy, by providing training and the most out-of-the-box experience possible. And we also are keeping an eye on cost while building and rolling this out. And for the future, we are thinking of, is there anything common, more common metrics such as drift that is very popular among all our data scientists and MLEs? Can we build templated dashboards for that? And as you saw, all of this is based on our analytics warehouse, which means that the most fresh data is about a few minutes or hours. So can we make that more real time? Yeah, that's what we have in store for the future. A quick recap. We looked at the context of the team and how ML is used in Loblaw Digital. We looked at some common design patterns for observability. We looked at a vision for a better solution, and we saw how we are rolling it out right now. Well, that concludes the talk. Thank you for your attention and time. I'm around today, so say hi, come talk to me, connect with me on LinkedIn, and I am open to questions. Thank you. There's someone here.
So you mentioned the recommender systems. Typically, I guess recommender systems are going to be using embeddings, like user embeddings, item embeddings, etc. One, is that the case? And I guess the real question is essentially, do you have embedding?
Can you speak a little louder? I can hear.
Yeah. Is it better?
Yep.
The question is, do you have embedding support? You mentioned recommender systems, and usually with recommender systems, you end up with user embeddings and item embeddings. I'm curious if there's embedding support into the logging.
These are not related to logging. We use these embeddings in our model serving APIs. You're right, like there's different types of embeddings, different versions of these embeddings with different architectures. We will measure, like you saw, we have annotations to each of our inferences as to which models serve these inferences. So we will know which embeddings produced which inferences. So yeah, we use embeddings and we have ways to measure them already, and with the centralized stack, we will make it even easier. Yeah.